Hello and welcome to today's webcast, Cooling System Filtration, Methods and Benefits, sponsored by Evoqua Water Technologies. My name is Angela Godwin. I'm Chief Editor for Water World magazine, and I will be your moderator today. A few housekeeping items before we begin. The slides for today's presentation will be pushed out to your screen automatically, and a PDF of those slides is available for you in the Event Resources tab in the console window. The presentation today is both live and interactive, so you can ask questions at any time by clicking on the Ask Question button in the presentation window. If you're running any pop-up blocking software, you will need to disable it to view the webcast. In addition, it's recommended that you close down all other applications for better performance. If you have any technical difficulties during the webcast, please type your issue into that Ask a Question box, and a member of our webcast support team will work with you to correct the problem. Also, a certificate of attendance will be issued automatically via email to all attendees. I'm sorry, not via email, but if you stay logged in at the end of the webcast, you'll see a congratulations message. It's very important. If you want that certificate of attendance, please do remember to stay logged in until you see the congratulations message. For your convenience, the presentation will be available on demand within 24 hours of the live event. A reminder email message will be sent out to all registrants with a link to the archive. It will also be accessible from our homepage at waterworld.com. We have two terrific presenters for you today. Walt Kozlowski is currently the Manager of Strategy and Growth at Evoqua Water Technologies and a former employee of Nalco and Calgon Corporations. He has over 25 years of water treatment experience in various positions, including sales, marketing, and environmental engineering. He is also the author of U.S. patent Methods of Inhibiting Fouling in Liquid Systems. We also have Bob Bradley. He is a recently retired engineer and technology manager with over 40 years of experience designing water treatment systems at Veolia, Indec, Hydrometrics, Permutit, and Nalco. He's published over 40 articles and papers on various topics in water treatment, and he holds 5 U.S. patents covering filtration, biological oxidation, and reverse osmosis topics. And now, without further ado, I will turn the program over to Walt.
Thanks, Angela. Before we get started, I'll quickly go through the topics that we'll discuss today. The presentation is divided into 2 parts. In part 1, Bob's going to review the causes and effects of the issues that you may encounter in your cooling system. He'll discuss the cooling water triangle and the factors that impact system performance, followed by why you should filter your system, and close with a discussion on fouling and microbial growth. In part 2, I'll take over and I'll review the guidelines for choosing a filter and also show you the various filter types available. We'll finish up the webinar with some time for Q&A. Now, one last note, there's some poll questions embedded in the webinar. We hope you participate in those questions, as they'll help us give us a view of what's going on and what issues are most important right now. So without further ado, I'll turn it over to Bob.
Good morning, everyone. We're going to first talk about cooling water problem, causes, and effects. There we go. Basic cooling water problems are, loss of heat transfer. The whole thing for a cooling tower is it's supposed to cool off a system or a process. And if you lose your heat transfer, you lose the whole benefit of having a cooling tower. Also, you can reduce equipment life with fouling in the system. You increase maintenance, you lose production, you lose profit. You can shut down the plant, and there's an issue with employee health. Cooling towers grow a lot of bacteria, and bacteria can cause health issues. Why filter a cooling water system? Contaminants enter the cooling system in a number of ways. The biggest issue is airborne contaminants. You got dirt, dust. If it's a construction site or near a construction site, this is a real problem. You also got pollen and biological things like ragweed, spores, seeds, whatever. And your makeup water can contain some dirt, and this should be filtered out. You also can get process leaks getting into the system. System performance can be affected by the dirt. Excessive contaminants in the cooling water can increase your chemical demand. It can screw up the chemical system. It can affect heat transfer. Contaminants can collect in low flow areas. And also you got an issue with health and safety. As I mentioned before, bacteria can affect people's health. Factors impacting performance: following microbiological growth, scale formation, and corrosion. Following, you have dirt, it spoils out the heat exchange. Microbiological growth can cause short-circuiting and mess up heat exchange. Scale is an insulator, and if it forms on the tubes of a heat exchanger, you lose some of that heat exchanger capacity, and your system can wind up being hotter than it was designed to operate at. The water treatment chemical programs helps control fouling, biological growth. You're feeding chemicals to help the cooling system work better. However, if you've got dirt in the system, that dirt can absorb some of those contaminants or chemicals and spoil out their effect. Makeup water quality can affect the contaminant load in the system. You put dirt in the system and the makeup water, it concentrates up and becomes a more and more problem as time goes on. We've got this triangle.
Bob,
Yes,
at this
ma'am.
time, I'm just going to jump in very quickly here, and I think this is a great time for us to do our first survey. We'd love some feedback from our audience there, and you'll see this popping up on your screen.
I'm sorry.
No worries. So we just want to understand what some of your greatest challenges are. If you would just take a moment and share your feedback via the survey, we would surely appreciate that. And then we will share those results with you, with our audience. And remember, too, that you can always ask a question at any time during the presentation through the Ask a Question box. Thank you.
Thank you very much, Angela. Can I go forward?
Sure, go right ahead.
Thank you. We've got a triangle. The triangle's got scale on one side, fouling on another side, and corrosion, and microbiome in the middle. Microbiome's in the middle because it aggravates all the above. Microbiome can cause scaling and fouling and corrosion, and so that's kind of the center of attention. Fouling is the accumulation of a solid material or other scale that hampers the way a cooling tower or heat exchanger operates and contributes to the deterioration. Some common foulants are silt, sand, mud, dirt, dust, seasonal contaminants like pollen or cottonwood, process contaminants, corrosion products, microbial growth. It's fouling. Factors influencing fouling include the water chemistry, the water temperature, the water velocity. When you get low flow areas, dirt tends to settle out in those areas and can cause short circuiting. Microbiological growth, corrosion products, process contamination, the tower's location. If it's in the middle of a construction site, you're going to have problems. Dirt, scale, foulants are insulators. The whole idea of a cooling tower is to transfer heat. If you've got dirt or scale forming on the tubes of a heat exchanger, you can't transfer as much heat. The heat capacity, the heat transfer rate for copper is huge compared to the heat transfer rate of other things. In particular, probably the worst foulant in the cooling system is microbial growth. The size of the particles also affect things. If you've got a half-inch marble in a system, you've got one particle. But if you dissolve that or disperse that same marble into 2-micron particles, you can have billions of them. So the big particles don't tend to cause a problem. They move through the system, get washed off, they don't stick to the tubes. But little particles stick to the tubes and form a film. Oops. Ways to prevent fouling: you can feed a dispersant. A good scale or corrosion control program. Clarify the makeup water. The cleaner the water you put into the system, the cleaner the water is going to be recirculating, because everything that you put into the system concentrates up. Another way to control dirt in the system is Sidestream filtration. And I think the Sidestream filtration is just the best thing you can do to make a cooling system operate much better. Ongoing control involves backflushing, baffles, air bumping. These are kind of band-aids to fix a dirty system. The easiest way to keep the system clean is keep the system clean. Use a Sidestream filter to continuously remove dirt. Again, we're going back to the triangle, scale, fouling, corrosion, all aggravated by microbiome. Biological growth in your system is the system itself, it's an ideal environment. You're operating at temperatures where bacteria love to grow, algae grows, particularly if you got sunlight on the deck of the cooling tower. Fungus grows, and fungus can be a problem because it eats wood. And you can destroy your tower lumber if you get fungus growing within the system. Microbiological growth, again, bacteria. Bacteria can be dangerous. They can actually make people sick. There's a disease called Legionella, which started in a cooling water system or an air conditioner and made a lot of people ill, killed some people. Also, bacteria can form slime. Some of them can be anaerobic. They're ion depositing, or nitrifying and denitrifying. And a quick story on nitrifying bacteria. A number of years ago, I was involved with a refinery that had a corrosion problem. Just all of a sudden, the spring of the year, all their heat exchangers was bringing leaks like crazy. And they asked me to investigate the system, find out what the problem was. And the first thing I wanted to do is look at the operator log. What's the pH? What happened to the pH? And how much acid you're putting in that cooling tower? I found out that the operator hadn't put acid in the cooling tower in 3 or 4 weeks. And he said, just when the ammonia leaks get right, it doesn't need any acid. That's a problem, because the bacteria were forming nitric acid under the deposits right on the tubes, and nitric acid eats holes real good. Microbiological growth, you could have algae. The easiest way to prevent the algae is cover the deck. However, sometimes that's not practical. Algae requires sunlight to live, so if you cut off the light, algae can form mats, fall equipment, and it can even be a safety hazard. Algae is slippery. If you're walking on the deck, you can fall down, and sometimes falling off a cooling tower is a long fall. Also, as I mentioned earlier, you can have fungi in the system. Fungus can eat cooling tower lumber. So controlling the fungus is important in a lot of cooling systems, most cooling systems. Microbiological growth can be affected by nutrients, ammonia, temperature. You're usually stuck with operating somewhere on the ideal temperature between 70 and 140, which is a good temperature for bacteria. pH 6 to 9 is ideal for bacteria. So they're pretty happy with the pH. Location is usually outside, in the light, in the sunlight. The atmosphere is normally aerobic. You're aerating the water. So the bacteria are very happy there. Problems caused by microbiological growth. Bacteria can form a sticky, slimy mass that spoils out the cooling effects. It'll short-circuiting within the system. It can plug a heat exchanger. Again, you could wind up producing acid from ammonia. You get iron-depositing bacteria, which can foul the system. I mentioned fungus can eat the cooling water and create food for other bacteria. Controlling microbial growth. I'm a big believer in oxidizing biocide. Keeping the water clean coming into the system is the first thing, and clean water generally has less food than dirty water. Dirty water is loaded with food and other microbiological growth, and growth begets growth. System design consideration often can aggravate the system. Minimize low flow areas. You want to keep the water moving. If the water is moving fast in the heat exchangers, the probability of forming a film on there is reduced. Oxidizing biocide, non-oxidizing biocide, biodispersant, it all helps. But again, chlorine is a key ingredient. Sidestream filtration. Sidestream filtration is the easiest way to take a difficult system and make it into a better behaving system. There's a variety of equipment choices, installation places. Generally, we're talking about filtering between 3 and 5% of the recirculating flow, and that'll really make the system operate much better. Continuously filtering can have a significant reduce of insoluble materials in the bulk water. The water treatment chemicals are more effective. Under deposit corrosion goes away. Water consumption is reduced because your blowdown's reduced. Blowing down a cooling tower to get rid of the dirt is not nearly as effective as filtering the dirt out. It's also cheaper because you stop throwing away all the chemicals. Sidestream filtration, it's been indicated by the U.S. Department of Energy and cooling tower manufacturer that this is a best practice. Baltimore Air Coil recommends mechanical filtration and water treatment specifically tailored for each installation. And you really have to look at the installation and the needs of the installation to decide what's the best Sidestream filter. And your equipment manufacturer is a good place to start. And now we're up to part 2. Walter?
Thanks, Bob. Yeah, I'm on. Thanks, Bob. Nice job. So before we talk about how to choose a correct filter for your system, I'd like to show you how the installation of a Sidestream filter can benefit you financially by addressing some of the issues that Bob mentioned earlier. So we've got an example here. And in this example, we have a cooling tower system that feeds a 400-ton chiller with a recirc rate of 1,200 gallons a minute. It's a seasonal tower, as you can tell, and it runs less than half a year. It's running at 70% load with an efficiency of 65%. This tower uses about $4,000 worth of oxidizing biocides per year, and it's cleaned 3 times a year by 2 employees, and you can see the cost a little over $4,300. So that's the setup. So we know that energy costs can be a significant expense in a cooling system, particularly when a chiller is part of that system. And in this example, the estimated annual energy cost is a little over $47,000. That cost is calculated using this simple formula you can see on the slide. It's tonnage times the kilowatt hours per ton times the load times how long you're running it times your cost for electricity. It's a pretty straightforward formula you can all use to calculate your energy cost for your particular system. So what's the problem here? In this system, the issue determined from a particle size analysis, which we'll talk about in a second, is that the particles in the water are down to 1 micron in size. And Bob said those small particles tend to stick first, and they're usually the big issue. And those particles are building up and creating a deposit 0.02 of an inch thick on the chiller tubes. Now we know that each 1,000th of an inch can increase your energy cost by 10% and potentially increase your chemical cost by 20%. Also, you may want to note that the ASHRAE handbook also states that a 200-ton tower can take in up to 600 pounds of particulate in a season. And obviously here we've got a 400-ton tower. So we're looking at as much as 1,200 pounds of particulate collected in areas like the tower fill and the sump and the low flow areas that Bob talked about earlier. So what do we do? So in this case, a filter is installed that filters 10% of the recirc rate. And remember, it's 1,200 gallons a minute is the recirc rate, and we're taking 10%, so it's a 120 gallon a minute filter. And that filter design that was chosen is going to remove that particulate down to the 1 micron. Again, the particle size analysis showed that's necessary. And after installing the filter, the particulate forming that 0.02 of an inch of deposit are gone, usually over a little bit of time. So this system gains back that 20% in energy it lost when the deposit was there. So that's about $9,500 in savings annually. Also, by removing that deposit, you're going to save on your oxidizing biocide. We talked about that. That removing that deposit improves your chemical performance. That's another $800 per year. And lastly, the manual cleaning of the system is conservatively cut in half. That's another $2,100 annually saved, all basically in labor charges. That doesn't include disposing of the sludge that you're pulling out. So in total, installing a filter in the system saves a bit over $12,000 annually. And again, this is a pretty small system. The filter that you need, again, is only 120 gallons a minute, and a savings of $12,000 annually will provide a very acceptable payback on the investment for most people. Now let's go over some rules to help guide you in picking a filter. First, look at your system holistically so you can pick a filter that best fits your conditions, your budget, and your goals. In regards to goals, the answer to how clean is clean is different for every system. I mean, having a pristine system is generally not practical and is usually really unnecessary. But consider the economics of not keeping a particular system as clean as possible. That's going to help you decide how clean is clean and how much you have in your budget. In general, in sizing a filter, you should take 3 to 5% of the system recirc rate. Normally that amount is going to be effective in cleaning up and maintaining the cleanliness of your system. You may have to go to a larger flow due to the particulate loading on your system. But remember, as you go larger, the filter cost is going to increase. And as Bob mentioned earlier, if you're next to a construction area or a farm, your loading is going to be higher. So you're going to want to go a little bit higher and oversize that filter a little bit. And also you have two options here. You could start with a clean system, or you allow the filter to clean it up over time. If you allow it to clean it up over time, you have to give it a little time. It's a little bit of a marathon. It could take a couple of months. Before you choose and install a filter, always run a particle size analysis on the bulk water. It's really a critical step. Review the particle counts and the volumes to see the whole picture. You don't want to install a filter that only removes particulate down to 75 micron when the bulk of your contaminants causing you problems are less than 10. Lastly, the filter is only going to remove what it sees. As Bob said earlier, the particulates tend to collect in the low flow areas, and they're going to stay there. Feeding a dispersant once in a while is going to help dislodge those particulates and get them into the bulk stream so the filter can remove it. When dealing with heat transfer equipment, understanding the relationship of total suspended solids and a filter's removal capability is key. As Bob also said, the smaller particulates tend to follow heat exchangers first, not the big ones. So if you only look at particle volumes and ignore the counts, you may miss that small particulate. You can see on this graphic on the bottom of the page, 9 ppm of a large particle is really not the same as 1 ppm of a bunch of small ones. You've got billions of those small ones that are going to start sticking. So before you choose a filter, remember to review the volume and the counts to have a clear picture of your conditions. There's many different types of filters available. Some of them have been around for quite a long time. There's high-efficiency sand filters, traditional sand filters, cartridge bag filters, cyclonic filters. Sometimes you hear those called centrifugal separators, disc filters, and last but not least, the self-cleaning screen filters. Each one of these filter types have pros and cons. So the best solution for your system depends on your conditions, your goals, and your budget. Don't just buy a filter because it looks flashy or maybe it has lots of bells and whistles on it. You may not be happy with its performance. It may not be sized properly. It may not have the removal efficiency for your conditions. So I think we've got a survey coming up.
Yes, Walt, I think this would be a great time for the audience to give us a little bit of feedback on what type of filtration systems do you currently have on your cooling system. You're going to see that survey pushed out to you. And if you would just take a moment and let us know your feedback, that would be very, very helpful. And while you're doing that, I do want to remind you that if you want a PDF of today's presentation, there is one available for you in the Event Resources tab. So we've got some results coming in, and we'll be sharing those with you all in just a moment.
Looks like excellent. So far, there we go. So we've got a mix of some people are using a good, about 30% are using screen filters. Cartridge and bags are still around, media filters, and it looks like about 10% are centrifugal separators. And another 30% aren't using anything. So that's it's interesting. So it's kind of a broad. Everybody's using a little bit different, which is not surprising. So, but we're going to talk coming up now on a little bit more on the filters and choosing them. So here's a matrix that everybody can use that shows all the various filter types that we just had on that survey. And it gives you a quick way of reviewing the features and benefits that a filter may or may not have. And I'm not going to go over all of these. You can see there's a lot of details here. But as an example, how to use the tool, you can see that cartridge filters have a low capital cost. And I think it was about 20%, 30% were using cartridge and bag filters. So they've been around. But remember, that low capital cost is offset by high maintenance needs. And the fact that you have to deal and dispose of those cartridges or bags. Some people reuse the bags, but it's also, it's a pretty dirty proposition to be cleaning out the bags and reusing them. And eventually they're going to have to throw them out anyway. And over the years, I've seen cartridge and bag filters installed on a lot of systems. The issue became companies got leaner, and maintenance guys didn't have time to deal with changing these cartridges. I remember one specifically, the maintenance guy was telling me that he's more worried about repairing pumps and seals and packing. He didn't have time to deal with a cartridge, so he kept putting it off and putting it off. So, and eventually they just bypassed it, and that usually is what happens. You just don't have the maintenance crews that can want to deal with changing these cartridges out, so they end up bypassing them or isolating them. So they may not be a great choice for you depending on your situation. If it's a small system, you could possibly use them if you're not, it's not a very dirty system, but the larger systems, as you can tell by the matrix, they're not really a great fit. Now, once you've got your particle size analysis, which I mentioned earlier, you can use this matrix to see which filter checks the boxes that are important to you. It'll help you with a selection. Now, this is a kind of a busy chart, but it shows you various particles from large to very small. The point here is that, generally speaking, in a cooling system, your primary concern is that 1 to 50 micron range. In some cases, it may be 1 to 100. Depends on the conditions. So you should choose a filter that's efficient in that range. You can install something like an RO or a UF. You can see it'll filter down to very small particulate. But and I've seen some people investigating that. But in most cases, it's really overkill, and it's going to be extremely expensive. The payback is going to be really not very good. It's like using a power saw to cut a piece of paper. Yeah, it's going to work. It's going to work really well, but it's really too much tool for the job. You can also see there's some overlap of filters in this 1 to 100 micron range. So again, use that filter matrix to help you with your decision and help check the boxes that are important to you. Also, work with somebody who understands filters and can help you pick the right one. As much as we all may love Amazon, and my wife's the first one that loves Amazon, but in this case, it's really not the best place to get your filter. So before we close, we're on the home stretch here, and there's a couple of Evoqua filters that I just want to touch on that have a good fit in cooling systems. And note that these filters check a lot of the boxes on that matrix. The first is Vortisand, and Vortisand is a high-efficiency sand filter that uses microsand to provide submicron performance. It's got a shallow bed, and it reduces footprint and uses less water for backwash compared to other media filters. It's also got a low electrical demand, and it may help you qualify for some LEED credits for your facility. Since they work well in that 1 to 50 and 1 to 100 micron range, they're a great choice for most cooling systems. The other one I'd like to touch on is the VAF self-cleaning screen filter. Now, these filters use a weave wire filter element. They're inexpensive, low capital cost, they're compact, and they can handle very high flows. You can connect them up in parallel, and they don't need much maintenance. I've used these quite a bit over the years. They're a good choice for cooling systems, but you got to note that if your particle size analysis shows that the bulk of your particulate is below 10 micron in size, these may not be your best choice because, again, they're not going to filter continuously below 10 micron. It's the smallest screen you can go with. So in those instances, go with something like a Vortisan. So in summary, we're getting near the end here. Sidestream filtration is a proven method to improve your cooling system efficiency. Both the DOE and the cooling tower manufacturers stand behind it. A cleaner system is going to work better. I mean, that's a pretty straightforward concept. I think we all get that. Sidestream filtration is going to support good microbiome control. It's going to minimize or potentially eliminate your cleanings. It's going to improve the effectiveness of your water treatment chemicals, and overall, it's going to reduce your overall cost of operation. But remember, a filter is not going to fix a mechanical issue that you already have. It's not going to fix a pump. It's not going to help tower fill stay in place if it's already starting to collapse or wood that's falling apart. Just view the filter as a key component that's going to help you get your most out of your system. Lastly, there's many different types to choose from. Picking the right one depends on your system conditions, your system size, your filtration goals, and obviously your budget. Well, that's all I got at the end of our formal presentation, so I'll turn it back over to Angela.
Thank you so much, Walt. Great job, both you and Bob. We just want to ask our audience one more survey question before we head into our Q&A session. We'd like to understand what some other topics might be that you would like to see in potential future webcasts, and we've got a few choices up there on the screen. If any of those, look interesting to you, if you would just check off which ones might be of interest, that would be very helpful for us. And while you're doing that, I will let you know we are going to head into our Q&A session. And if you have a question in mind, you haven't had a chance to ask it yet, you still can do that through the Ask a Question button. And whatever questions we don't get to today, we will share with our presenters, and they may be able to answer those offline. So don't despair if we don't get to your question today. And so with that, we have your results. Thank you very, very much for sharing that information with us. So let me go ahead and get into our Q&A session. We've got quite a few questions lined up. And let's start off with something kind of basic. You guys talked a lot about Sidestream filtration. Could you elaborate on that and explain a little bit more what that is?
So, Angela, I'll jump into that. So side-stream filtration is just that. It's taking a side stream of your recirculating water flow as opposed to full flow filtration, which you could do. Some people have done that. So and then that's essentially installing a full flow filter that's going to handle. So if your recirc rate's 1,200 gallons a minute, you can have a filter that filters 1,200 gallons a minute. Side stream is just taking a little bit split. It's a slipstream of that flow. So it's an effective way of cleaning up your system over time, but it limits the amount of money you have to spend on a filter. So it's, and again, you could do that same side stream or full flow on your makeup water. Bob talked about, cleaning up your makeup water is a great way of controlling particulate in your system. You could do side stream or full flow on your makeup water as well.
Excellent. Great. Thank you. And this is sort of a related question that came in. Do you recommend UV disinfection in your side stream?
I think I'll take this one first, Bob, and maybe you might want to comment. UV, yeah, you could. UV has been around, ultraviolet light for those who aren't familiar with that, and it is used on some systems. It's very effective. It does do a nice kill. It's got a little bit good performance, but some of its cons would be on a very large system, you're going to need probably a bank of UV lights. And you've got to keep them clean. So a lot of manufacturers, including us, Evoqua, we've got a system that helps clean that cell. The lamps do have to be replaced over time, but if you're looking for a non-chemical approach, it is effective. It's growing in popularity, and you kind of balance that with the cost of installation and maintaining. Any thoughts, Bob?
This is Bob, and I've got a comment on it. It's if you're going to UV the entire cooling flow, it's going to be effective. But if you're thinking about UVing a side stream, if you only kill a percentage, they'll come right back and grow. I mean, once they get back into the bulk water and mixed up with other bacteria grow at amazing rates. And it's at a side stream on UV, it's just not effective. I'm
Great
done.
point, Bob.
Okay, great. Well, let's go ahead and move along then. Let me pose this question for you. Would oxygen control at 5 milligrams per liter or lower in a closed circuit be the best option to avoid all the possible issues mentioned on cooling systems?
I could take it or you can, Bob. It's up to you.
Yours.
So you can have, bacteria don't necessarily need oxygen to grow. You've got anaerobic bacteria that will survive in an unoxygenated environment. So you're going to solve one problem, but you're not going to solve the other one. So no, it's not really a good process to just deoxygenate a cooling water system. It's not going to solve all your problems.
Some of the biggest problems you wind up with from a bacterial standpoint is anaerobic bacteria. They tend to be corrosive bacteria. And in an oxygen-free environment, that's what grows. So, yeah, well, not really, is a solution.
Okay.
Done.
Terrific. All right. Well, let's tackle this one then. When a customer has a cooling tower system that's running without a good treatment program and several rust areas are present, what's the best process to remove rust and start a good treatment plan?
Well, so it depends on how far the rust is gone, and it depends on your materials construction. Are you talking galvanized? Are you talking cast iron? Are you talking steel, etc.? I mean, I don't want to get too far into the weeds on that. I mean, you really need to find yourself a good chemical water treatment company. That's
when you get in.
You would want to work hand in hand. The equipment works hand in hand with the chemical program. So you're going to say something, Bob?
Yeah, when you start up with a new cooling system, one of the most important things you can do is pre-treat the exchangers with a phosphoric acid compound. There are a number of exchanger pre-treatments that contains high amounts of phosphate. They will remove rust. That's what they're for. If you can shut down your cooling system, if it's a corroded up system, I would shut it down, clean it thoroughly with a phosphate cooling water system cleaner, and then go back online with a good chemical treatment system.
Just be careful. Obviously, again, work with a chemical. Don't do that on your own.
You could spring a bunch of leaks.
Exactly. You'll start. Sometimes that rust will hide. Is just barely holding the metal together, and you'll end up breaking free a lot of leaks, and your heat exchanger will turn into Swiss cheese pretty quickly. So yeah, again, can't emphasize enough. Work with a good water treater.
Okay, great. You talked a lot about particle size analyses, and we had one audience member that was wondering what kind of firms perform particle size analysis.
Okay, couple options there. I mean, so there's labs out there. If you Google it, literally Google it, you'll find labs that'll do that. The trick is understanding how to see them. I mean, I've seen hundreds and hundreds of them, and I kind of have a feel for what they look like, what a good one looks like, what a troublesome one looks like. So, I mean, just running it is not the only concern. It's understanding what it shows. So, again, the water treatment chemical providers can do it. Equipment providers, again, we can do that, and that's part of a service we provide before we put a filter in. That's what we're going to do for you, and us in particular, Evoqua, we're not going to charge you for that. It's part of the program. So, don't try to do it on your own. If you do it, you may not understand what you're going to read. It's a analytical analysis report that, unless you've seen them before, you may not understand what you're seeing.
Mm-hmm. Okay, great. Thank you. Another question from the audience. Are there issues with filtering less than 3% of flow?
Other than it's going to take you longer to clean up your system, or it may not maintain. Again, like Bob said, I mean, if you're next to an area that's collecting a lot of dust, and those cooling systems are air scrubbers. So less than 3%, you're really not saving a lot on your equipment cost, and it's probably not doing a heck of a lot. It's only, think about it. You're collecting 1 or 2% of your total flow. and you're still pulling in all kinds of dust, it's probably not going to have much of an impact at all. 3% is really the bottom end to have any kind of an impact from a filtration standpoint, up to 5%. Also, one note on your closed loops. A lot of times on closed loops you can go pretty high. I think I have a note in there on one of my slides that you can go 10%, you can go higher on closed loops, because usually closed loops are smaller and their flows aren't as big. Also, a lot of times on closed loops you don't need to do continuous filtration. If you've got a good water treatment chemical provider that'll help maintain that system and keep corrosion down, a lot of times for a closed loop, installing a filter for a period of time, maybe a few months, just to do a cleanup, freshen it up, is enough, versus open loops where you really need that continuous filtration all the time.
This is Bob. I've seen beneficial results at 2%, but only in a very clean environment. If the wind coming by is, really clean air, you might do it with 2%, but that would be the exception and not the rule.
And realistically, unless you've got a huge system, going from 2 to 2 to 5 on your filter size is really not increasing the cost of the capital cost that much. It's pretty insignificant.
Okay, great. Thanks, guys. How about this? I have screens in my tower sump. Is that good enough for tower filtration?
The screens are there to collect. Go ahead, Bob. Yeah, go, Bob.
The screen picks up ragweed and cottonwood and stuff like that, but it really doesn't affect the dirt and particles and the stuff that fall exchangers. I'm going to say categorically that screens are inadequate unless you got something like a 1 micron screen in a filter device. Done.
Okay, great. Thank you, guys. Is there a specific microorganism that causes the bulk of fouling, or is it really just a mix?
It's kind of a soup. There's no one. Some of them cause more issues than others. I mean, Bob mentioned Legionella, and that microorganism does cause a lot of problems. And we're not going to touch too heavily on that right now, but there's some that are worse than others. But in most towers that I've experienced over the years, it's really a soup. It's a mixture of various things.
Okay, great. Thank you. Now, if I install a filter, how do I know that it's working properly and making any difference on my system?
So, 2 ways. I mean, visually, but visually is not a great way because you're only really seeing, maybe a small fraction of the system. Really, the best way is you're going to do that particle size analysis before you install the filter, and that's a baseline, and then install it again in 60, 90 days. Run the particle size analysis again in 60, 90 days after the filter has been installed, and you're going to compare results. And then maybe do it again annually after that. You also might see over time, you'll see your chemical usage drop a little bit, your biocide use drop a little bit. That's going to be an indicator as well. But realistically, I'm all about data, and the particle counts are going to give you a good hard data on what's going on.
This is Bob. I'm going to suggest you run turbidity. And turbitometers are fairly inexpensive and they're readily available, and that's something you can take a number and log it in and keep track of that on a basis and maybe correlate some of your following issues to turbidity. But you can run, particle size analysis. That's a little harder. You can't run that in the operator shed, but you could do turbidity in the operator shed.
The only thing and I agree, Bob, and the only thing I would say, though, is don't look at it from a day-to-day, trend it over time, because there may be a few peaks and valleys depending on, what's going on in the system. So kind of, watching it over a trend of turbidity is another good way. Good point.
Yeah, you're going to see highs and lows. Spring is going to be a dirty point, and winter will be a low point.
Okay, great. Thank you, guys. All right, next up, what kind of filter system is recommended for particles less than 50 microns?
Well, there's a family of them. So again, those self-cleaning screen filters will filter down to 10 continuously, and below 10 at times. They build up a little cake. The high-efficiency sand filters will absolutely do that. They'll filter down to submicron levels. Water sand, as I mentioned earlier. Cartridge and bag filters. You could put a cartridge filter in at a half a micron. But again, we talked about the cartridge filters. The disc filters will do it as well. So there's at less than 50, there's a whole family. It's just you're gonna, but the prices vary, and again, maintenance demands vary. The size of the units vary. So you kind of it's not just there's not just one I can point my finger to. It depends on your situation, how much money you got, really, how much money's in your budget to spend, how much space you have, and the overall conditions going on in your water. So there's a lot of them. This is the answer.
This is Bob. I'm a big believer in high efficiency sand filters, media filters of some sort.
Yeah, and I would say, and that's a good point, Bob. And the regular sand filters, I mean, you could go down to Home Depot and get it, and it's not going to work very well. It's not going to filter down to the levels. Again, we talked about the real small particulate. Just a regular media filter is not going to do it. You need the high efficiency sand filter. It's really the best one to choose from. The water sand type is the best filter for your cooling water system. And again, you're going to balance that with some of the other factors if you've got the space for it. Most places do. So hopefully that answers that.
Great. Yeah, thanks, guys. And actually, this question is it's a nice segue into this one. Are there any applications where a combination of filter technologies would be used?
Yeah, possibly. I mean, you could have, again, if you've got a coarse filter followed by a vorticen as an example, a fine filter, that'll take some of the burden of the larger particles being caught by this ultra high efficiency filter. It's a little unusual, but it can be done. So you could have a screen filter. If you've got a lot of, your particle size analysis shows that you've got a lot of stuff in there, big stuff, small stuff, from a particular sizing standpoint, putting just one filter in there, like a vorticen, it'll definitely handle it, but it might run a little bit better if you put something a little bit coarser ahead of it. Again, it's a little unusual, a little bit more of a spend, but sure, it could be done. It depends on the situation.
As a rule of thumb, I'd rather go to 6% filtration or 7% filter than put multiple steps in there for filtration. But
agreed. I mean, it's easier to install. Just oversize your filter, and you'll be in better shape. But you absolutely can do it. You could do it in stepwise fashion, and actually, there's a way of doing it where you could have it operate seasonally. Have the coarse one, and I'm calling it coarse, but let's say it's a 50 micron screen during the winter, and it'll take your ultra efficient one, your vorticen, won't need to operate very much, so it'll take some of the burden off. But yeah, I'm with Bob. Oversize your filter, spend a little bit more money, and actually you'll save money by doing it that way. Just put one good-sized one in there.
Interesting. Speaking of filter proportions, we had a question come in. A general Sidestream filtration proportion was given as 3 to 5%. The audience member is wanting to know what the basis is for this rule of thumb, and how can one determine the design flow rate based on data gathered from the cooling water?
So the 3 to 5%, where it came from, it's, I guess, from the filter manufacturers over time. Data collected, it's kind of a balance, as I said. I mean, it's you might say that it's experience. Over time, you need a certain size of filter that's going to maintain your system cleanliness and keep up with the dirt load.
You could find several dozen papers written on the subject by the Baltimore Air Coil or the International Water Conference. There's just a bunch of papers written on that 3 to 5%.
Yeah, I think it's basically from data over the years, and again, it's going to vary. That 3 to 5% is going to, like Bob talked about, go oversize it if you've got a lot of dirt coming in. So that 3 to 5% is a kind of rule of thumb. It's not an absolute.
Okay, great. Thank you. We had a question come in about water consumption. How much water is used for backwash on Sidestream filters?
Depends on the Sidestream filter that you're using. So it could be anywhere from depends on the size of the filter. It's a tough question to answer, but some use less than others. So some of them will use the actual process water For instance, like the Vorta sands are set up that if you've got a duplex, as an example, the second unit will actually use the filtrate from the first unit to backwash itself. So it's really not using any additional water. It's not using fresh water. The self-cleaning screen filters will use the processed water and dump a little bit of that. So it's a little bit different. Some will use more. I mean, a traditional sand filter is going to use a lot of water depending on how dirty it is. It's just not designed
Another thing to consider is backwash water off the filter counts as blowdown. So
Exactly.
if you blow it down, put directly down the drain, or run it through the filter first, it doesn't matter.
So it's a great point, Bob. So when you first install a filter, and I've done this many times, sometimes you'll see your cycles of concentration drop slightly. And if that's an issue, you can throttle back the flow to the filter, but usually it's not. It's because it's only a brief period of time. But what happens eventually is you reach a state of equilibrium where that backwash water going down the drain is basically taking over for your mechanical blowdown. So your blowdown valve is really not opening because the backwash is taking care of it. So you're really not using any more water than you normally would.
Excellent. All right, great. Thanks, guys. Here's another question from the audience. Is chloride corrosion a concern with high rates of oxidizing biocide?
Oh, absolutely. I mean, yeah. I mean, talk to your chemical water treater about that. But yeah, you start fitting a lot of bleach. I mean, it's funny. A quick example. I was at a site, a food processing plant, a few years ago. That as I'm walking, they were looking at installing a Sidestream filter, and I'm walking up to it. I couldn't even see the tower, and I'm smelling bleach. I mean, it was overwhelming. And I walked up to it and I said, it looked turbid, and it smelled like a hot tub, quite frankly. And the operator's like, well, we don't have any microbial problems. I said, well, yeah, I can see that. Nothing's going to grow here. But I said, what are your corrosion rates? He said, well, yeah, we're having a lot of leaks throughout the system. That's why they're thinking about installing a filter. And I said, well, you're solving one problem but creating another. So it's, yeah, absolutely. Chlorine, like Bob said, it's a great tool. Bromine, another good option. It's probably a better option in many cases for controlling bacteria. But it's one of those cases where too much of a good thing is not a good thing. So it's overfeeding, oxidizing biocide is going to cause corrosion. No two ways about it.
For the most part, the chloride that causes the corrosion is coming in with the makeup water and concentrating up. It's not from the chlorine you're feeding. If it's from the chlorine you're feeding way too much chlorine.
Yep.
Okay,
and I've
great.
seen that.
Thank you, guys.
I've seen it where people just turn up the pumps and start cranking it up, and all of a sudden they got leaks. So yeah, be careful of that. Work with your water treater.
All right. Well, next up, are there any Sidestream filters that can remove small amounts of oil and grease, like say 10 parts per million, or is 10 parts per million not really a problem for cooling towers?
So 10 parts is not an enormous amount. Something like now with a media filter like a high efficiency sand, Vorta sand, or other media filters, a little bit of oil is a small amount of oil is generally not a problem, but 10 parts is probably starting to push it. You'll end up coating the media and it becomes difficult to clean. In those cases, you could use a self-cleaning screen filter. They'll handle maybe 20, 25 parts of oil without starting to plug themselves up. The whole issue is that oil gets sticky. It gets with the particles and it gets sticky, and it becomes hard to clean. It's not so much removing it; it's cleaning the filter. So oil's a tough one. If you've got, like in a refinery, if you've got a lot of oil coming in, I mean, good clarification ahead of it. You could use a bag filter, but again, then you got to dispose of the bags and everything. So good clarification, a good water treatment program that's going to disperse that oil and keep it from getting sticky is going to be your best bet. But 10 parts. There's a couple of different options. Like I said, media filters borderline, self-cleaning screen might be a good choice.
The other thing is if it's a short-term, and hopefully it is a short-term thing where you're just going to try to clean it up in a shot for a week or whatever, a little bit of powdered activated carbon works. But you need a Sidestream filter to take it back out again. But the carbon will absorb the oil, and you can get it out with your Sidestream filter. Now
remember, that oil, though, is going to be great food for bacteria. So it is, 10 parts of oil, you may say, I said it's a small amount, but that's a good base for a food for that bacteria. So it's
you could turn a cooling tower into an aeration pond real easy.
Exactly. So it's going to increase. Try to keep an eye on oil. If you've got oil contaminants going in there or potential for that, keep an eye on that because it's going to cause you a lot of problems, increase your bacterial loading, like I said, and it's going to make your chemical costs go up pretty high. So keep an eye on that.
Great. Thank you guys very much. Is there a filtration system that will take care of metals like copper, or will that just go as part of the suspended solids?
So if they're suspended copper, insoluble copper, yeah. I mean, it's the filter doesn't care so long, what the particulate is, just so long as it's insoluble. So if it's soluble copper, that's something different that you're talking about, and that's a completely different type of filter that now you're stretching into the realm of RO, et cetera, and maybe a chemical program. But insoluble, yeah, it's all about the particle size, and choose your filter for the particle size. It doesn't care what that particulate is.
Copper is normally a blowdown/wastewater issue. And there are specific ion exchange resins that'll pick up copper specifically out of a blowdown stream.
The one thing to note, though, if you've got copper, keep an eye on that, obviously, because you're going to want to know where that copper's coming from. So if your copper's coming from your makeup water, that may not be a problem. Like the city of Chicago, where I'm at, there's a certain amount of copper in there just in the piping. But if your copper exceeds, your copper in your tower is exceeding what your makeup water is providing, now you got a corrosion issue. So it's an indicator.
Great. Thanks, guys. We're coming up to the top of the hour very quickly, but I have time to throw just one more question out there before we wrap up. What makes a sand filter high efficiency?
Well, it's all about the sand. It's a couple things. So water sand uses a microsand. It's a very, very small particle size of the sand. So it's you've got very small gaps, if you will, in between each particle of sand. So it's about the sizing. And high efficiency also encompasses how much water it uses for blowdown, how much electricity it uses. So high efficiency is about how it filters, but also how much energy and water it uses. So it's kind of a two pieces right there.
Terrific. Great. Thank you so much. With that, I'm going to start wrapping things up because we are getting to the top of the hour and we want to be cognizant of people's time. But I do want to let you folks know that if you asked a question and we didn't get an opportunity to answer it, and there were many, many, many good questions that are still remaining in the queue, we will send those over to the presenters, and they perhaps will be able to answer those for you offline. And thank you all for entering your questions. We appreciate that. And with that, on behalf of Penwell Corporation, I just want to thank today's speakers, Walt Kozlowski and Bob Bradley. Terrific job, gentlemen. And I want to thank our sponsor, Evoqua Water Technologies, for today's presentation, which was called Cooling System Filtration, Methods, and Benefits. And remember, this presentation will be archived within 24 hours. You can access it from the homepage at waterworld.com. A reminder email message will also be sent out to all registrants with a direct link to that archive. And just real quick, don't hang up or disconnect. If you want that certificate of attendance for today's webcast, just be sure to stay logged into the presentation until you see that congratulations window, and that will let our system know that you want a certificate, and we will send that out to you via email. So once again, we want to thank you all for joining us today, and we look forward to serving you with future webcasts. This concludes today's presentation.
Interesting.